In order to know what direction an ion would actually move, we need to calculate its equilibrium potential. That is calculated using an equation called the Nernst equation. And the Nernst equation takes into consideration both driving forces, diffusion and electrostatic pressure. When we measure the equilibrium potential for sodium using the Nernst equation, we find out that it is approximately 60 millivolts. Another way to think of that is that sodium wants to be in a cell, or sodium wants the cell to be at plus 60 millivolts. Okay? When the cell is at plus 60 millivolts, sodium is happy. If we look at the range of membrane potential, let's say plus 60 is up here, minus 70 is down there, and sodium is a positive ion. So if a neuron became permeable to sodium, it would enter the cell to drive membrane potential less negative and ultimately more positive until plus 60 millivolts is reached. However, now let's say this is plus 100 plus 60. We can leave this at minus 70. If for some reason our neuron were at plus 100 millivolts, sodium still wants the neuron to be at plus 60. So now sodium would have to leave the cell, the positive ion would have to leave the cell in order to drive membrane potential from plus 100 to plus 60 millivolts. Okay. We can do the same thing for potassium. Using the Nernst equation, we find out that the equilibrium potential for potassium is around, sorry that was weird, equal sign, is around minus 90 millivolts. Okay? So we can do the same thing, right? Here's membrane potential looking at just a y-axis. Plus 60, minus 70, minus 90. Okay? And again, this is calculated using the Nernst equation. So the Nernst equation tells us that the equilibrium potential for potassium is around minus 90 millivolts. Okay? So this is also a positive ion. And if potassium wants the cell to go from rest to minus 90, that positive ion needs to leave the neuron to make the neuron more negative. Okay? Let's do the same for chloride. I don't know why I can't draw equal signs. The equilibrium potential for chloride, for the purposes of our classroom, is going to be minus 75 millivolts. All right, let's put it right here. All right, chloride is a negative ion. So if chloride wants the cell to go from minus 70 to become more negative at minus 75, chloride needs to enter the cell, right, to make the cell more negative. Once we understand our two driving forces, we can apply it to any situation, right? Remember, our driving forces are diffusion, which is movement from a high concentration, these brackets just mean concentration, to a low concentration, and electrostatic pressure, movement based on charge. Opposite charges attract, and like repel. Right? And then we can use the Nernst equation, which considers both diffusion and electrostatic pressure to provide us with an equilibrium potential for an individual ion. We know, using the Nernst equation, that at body temperature, the equilibrium potential for sodium is about plus 60 millivolts. For potassium, it's about minus 90 millivolts. And for chloride, for the purposes of our class, we said it's minus 75 millivolts, right? So we know that our resting membrane potential is around minus 70 millivolts. But let's say we're not at rest. Let's say we are at plus 60 millivolts. Now let's look at how the forces for sodium change when we're not at rest. We still have a ton of sodium outside the cell, just a little bit of sodium inside the cell. So if we look at just diffusion, sodium's going to want to move from a high to a low concentration. But if we look at just electrostatic pressure, the positive inside of the neuron is going to repel the positive charge of this ion. And based on just electrostatic pressure, sodium would want to move out of the cell. Now I've set this to 60 millivolts because that is the equilibrium potential for sodium. What that means is that at the equilibrium potential for sodium, which is also called the reversal potential, at this potential, the force of electrostatic pressure on sodium is equal and opposite to the force of diffusion on sodium. So even if we open a big old ion channel permeable to sodium and allow sodium to go in and out of the cell at will, there will be no net movement. That would be like when it's 60 degrees outside the house and 60 degrees inside the house. Even if you open all your doors and windows, the temperature inside your house is not going to change. Now let's take a look at what happens for potassium if the cell is at plus 60 millivolts. We have more potassium inside the cell than outside the cell. Based on diffusion, we're going to want to move from a high to a low concentration. Based on electrostatic pressure, again, the positive inside of the cell is going to repel the positively charged potassium ion. So when we're at plus 60 millivolts, both electrostatic pressure and diffusion are pushing potassium out of the cell. That will help potassium drive membrane potential from plus 60 to its favorite membrane potential of minus 90 millivolts. We can do the same thing for chloride. We have a little bit more chloride outside the cell than inside the cell. Diffusion moving from a high to a low concentration. And electrostatic pressure, now in this case the negatively charged ion is going to be attracted to the positively charged inside the cell. So electrostatic pressure would be pushing chloride into the cell. The negative ion entering the cell will help chloride move membrane potential from plus 60 towards its favorite membrane potential of minus 75 millivolts.